I don't know. Nothing's coming into focus.
Have you tried wearing your glasses?
Hey everybody, welcome to another walkthrough. This week we're going to be going over reflection and refraction, the particle nature of light, where we'll be looking at geometric optics as our evidence of the particle nature of light. I'd like to welcome Garrett this week to helping us out. He's going to be going over the theory and talking you through some of the concepts that we'll be using to explore the particle nature of light. But before we do that, let's talk about this week's PreLab activity. In this week's PreLab, what you'll be doing is a very straightforward process of looking at refraction and reflection with surfaces. What you want to look at is placing an object into a cup of water. You want the cup of water to be fairly tall because what you want to look for is the separation of the object that's in the water and the image that we see coming out. And when you're straight on, you should see that it's fairly lined up. This is magnified because it's a curved surface. If you'd like to check the magnification, you can calculate the magnification by measuring the width of the pencil and then the actual pencil and measuring the apparent width of the pencil in your eyes. Then you'll rotate the pencil and cup 90 degrees, at which point you should find that the light is maximum displaced, because over here the curvature is so intense compared to the pencil and the light coming out of the front end that it has given the impression that the pencil is separated from the top and the bottom. Of course, this is an optical illusion, but the entire point here is that this is due to the ray optics. So you take a picture of this in this form as well. Your final picture will be taking the picture from above, and the idea here is that you will draw lines of light coming out and heading out towards your eye, which is outside the cup. The idea there is to demonstrate the refraction of light. Finally, there's one last picture you want to take that will complete your PreLab demonstration, and that is to go to a window of some sort, a nice flat surface, or even the curvature of maybe the window of your car or somebody's car that has you have their permission to do this. And you want to take your image just so that you're looking at a reflection of light off the surface of glass, which when you're looking straight at it, you can see straight through. But you want to be at an angle that's high enough that you can see the reflection like trees or street lights or whatever the case on the surface of the glass. And that will demonstrate that light does bounce off of glass, even though majority of it does go through. The actual number is close to 96% of light passes through, but about 4% reflects off the various surface. Excellent. Okay, so now that you've got an idea of how to do the PreLab, let's go ahead and talk about the theory with Garrett. Garrett?
Okay, so I'm going to be talking a little bit about the theory behind reflection. And for this particular experiment, we're going to be focusing on the particle-like nature of light. And I just so happen to have a ball to help visualize what's going on here. So the particle of light is going to follow all the basic laws of momentum that you've already learned. So for example, here in this diagram, if you have a particle of light come in at an angle, it will reflect off of this surface and it will keep the exact same speed as it came in from due to the laws of momentum in collisions. The angle that the particle comes in is known as the angle of incidence, and that is measured with respect to this normal line, which is perpendicular to the reflective surface. And then once it reflects off the surface, it will reflect off of the exact same angle as the angle of incidence, and this angle is known as the angle of reflection. And in this case, the angle of incidence is equal to the angle of reflection. Okay, so now that you know some of the basics about reflection, now we can talk about how to draw ray diagrams. And ray diagrams will help you determine where your image is located. Okay, so I'm going to walk you through the steps of drawing a ray diagram for this example here. So in this case, you have here this yellow arrow right here is your object. And the first step you're going to do is you're going to start at the top of your object and you're going to draw a line parallel to your principal axis. You're going to draw a line and it's going to collide with the mirror here, and because at the surface of the mirror is a flat surface, it will reflect off at an angle and it will travel through the focal point. Once you've drawn the first ray, once again you're going to start again at the top of your object, and this time you're going to draw a new ray straight through the focal point, and it will reflect off the mirror and it will reflect off parallel to your principal axis. Now you have one final ray to draw, and once again you're going to start at the top of your object. This time you're going to go through a point known as C, which is known as the radius of curvature. And you're going to draw it straight through that line, and it will reflect off the mirror and return straight back to where it came from. Now that you've drawn all your rays, you will see that they have all converged on one point, and that point is where your image will be. And so you can see that in this case, the top of your image is below your principal axis, and you will notice that the height of the image is different than the height of your object, and your image will appear inverted as opposed to your object. You'll notice that your image is at a different position from the center of the mirror, and that quantity is known as Q, which is your image distance, and that is your distance from your image to the center of the mirror. And another important value here is P, and that is the distance from your object to the center of the mirror. And we will see how to use those values in a moment. So I'm going to talk a little bit about the theory of refraction now. And again, we're going to be focusing on the particle behavior of refraction. And I will say that both reflection and refraction both can describe both the wave nature of light and the particle nature of light. So if we take a look at this diagram here, the first thing I will point out is that something that's very important with refraction is different mediums. So in this example, we could think of this empty area up here as air, and we could think of this blue area as any other medium like glass, for example. And these two mediums will have a value known as n, and n is known as the index of refraction. The index of refraction is defined as c, the speed of light in a vacuum, over v, the speed of light in a medium, which is always slower than c. And as a result, n is always greater than 1. All right, so in this case, we have our ball again, and if we have a particle of light comes in and it hits a certain medium, in this case glass, it will slow down and change its angle. And since it slows down, it has to come in towards our normal line. So therefore, the angle of incidence will not equal the angle of refraction. And there is a relationship between the angle of incidence and the angle of refraction. And this is what is known as Snell's law. And Snell's law can be defined as the index of refraction of your first medium multiplied by the sine of the angle of incidence, which is equal to the index of refraction for your second medium multiplied by the sine of the angle of refraction.
Excellent. Thank you very much, Garrett. That was a great explanation. Okay, so now that we're getting ready to get into the actual experiment, let's talk real quick about the lab report. The lab report is a worksheet style lab report, just like you've done in the previous semester, which means that as you did last semester, you'll take the worksheet that you've done in class. Then you'll prepare a one-page summary. Now on this page, we want to go a little bit beyond what we did last year. You want to talk about your results. Don't just submit the results, say here they are. We want to talk about them. Did you demonstrate the particle nature of light? Did we show that light bounces off in reflection, an angle in and angle out? That Snell's law applies for refraction? Were you able to demonstrate focal points for thin lenses? Make sure that you talk about any kind of errors that may have come up in the lab, anything that caused problems, just as we've done before. Remember, you want to zoom out and talk about, was this lab viable? Was this lab effective for determining the theory that we put forth, which is that light behaves like particles? For this week's laboratory, you'll be working with some optics, which includes reflective surfaces and refracting materials. The first object that we'll work it with is this three-sided triangular reflective mirror. One side is a flat mirror, perfectly flat. Side number 2 is a convex mirror, comes bending outward. And then the third one is called concave, where it bends inward. And one way to try and keep track of those is that for a concave surface, it's kind of like being inside of a cave. So it's got a curved inward curvature. Our second object is a trapezoidal piece of plastic that light can pass through, and it has different surfaces with different angles that light can enter and interact slightly differently with the surface. Our last two are both lenses. They both have a curved surface that corresponds to a single curvature of radius for both sides. One is a convex thin lens, the other one is a concave thin lens. So let's talk about the source. Here we have a light source that seems nondescript, kind of funky looking, but when you put power to it, it becomes a multifaceted light source. So you have a straightforward bright light source. On the flip side, there is an object. This has, as you can see, grades on it that are millimeter markings that you can project and measure onto a screen. On the front side, there are 4 different possible options. You have a single slit. Similarly, you can look at 3 lines of light coming out or 5 lines of light coming out. And again, you can use these for ray optics analysis. When it's time to start taking data, and in this case, you'll be marking data, take your first sheet, and you'll notice that you've got a couple drawings here of the outline that matches your triangular shape. And it's just simply a matter of matching it to the orientation that you see on the page. Now, the shape on the page is drawn using a slightly different curvature, but just make sure that you get, for each side, the main point is for the flat side, you have it flush with the line. For the curved side, you just simply make sure that they're about as flush as you can. But once you get it there, you want to kind of hold it in place, or maybe have your partner hold it in place while you make the rest of the measurements and markings for the next couple minutes. The goal here is to try and make sure that this normal line, this center axis, is aligned with the edge of your surface in such a way that it's at a right angle. Best way to find out whether it's at a right angle is to use your light source. With the lights off, you come in with your your light source. You see how it reflects off. You can see the beam path in the incident beam. You can see the reflected beam. And so with it held in place, what you do is you align it so that your incident beam goes right down that center line as best you can. And you can barely see in this image, but when you're working with it, it'll come back off and there'll be a slight misalignment. And you just adjust it until the reflected beam and the refracted beam are right on top of each other, and refracted beam, reflected beam are bouncing off of each other. Comes in, bounces off, and goes on along the same path it came in. So then once you've aligned that, this is aligned, and you don't want to move your optic at this point for that surface. You just simply pick a random angle. Just make sure that it bounces off right at the point of the surface where it meets at that normal line, the dashed line that you see there. You then mark along the beam line little dots or little dashes, just so you can mark a pathway with good accuracy along the beam path. Bear with me, I'm using my left hand here. And then you can take the light and use a straight edge to extend that. Now I'm using pen here because it shows up better for you on the video, but in your case you'll want to use a pencil. We mark it as far as you can on the paper. Try and make sure that they meet at that point. And then you want to stretch this out also, just so that you have that line. And then you place a protractor in place right at that point. Make sure that it passes through the 90. That's good. Now you've got this angle here that you can measure. So this is, instead of being, here's 90 degrees, 10, 20, 122, about 23. You may have a little bit more space on your paper, or you can use another sheet of paper to extend it for a moment. 23 degrees, and then over here 10, 21 degrees. And so maybe this is that lets you know what these are, maybe a little bit out of alignment. But and that's when that's why with the pencil you can erase better. And you do the same thing with each of these sides for the angles of incidence and reflection, because this will be incidence, this will be theta reflection. Every time you make a measurement on each of these sides, you record it in this part of the box, compare those using percent difference, and then you record that in the percent difference column. Next is to find the focal length of the 3 sides. Now, you'll notice immediately that for the flat on your table, it's already indicated as NA. That's because the surface of curvature for a flat surface is basically infinity. You have a radius of infinity, therefore you have a focal length of infinity. You can just write infinity and fill that in for these two items. But take your optic, place it in, set it in place again. This time we have 3 lines. You can see carefully, I'm going to turn the other light off just so you can see it more clearly. I'm going to zoom in also. You can see the incident lights, 1, 2, 3, and the weaker reflected beams that come back and crisscross with each other some distance away from the optic. You can pull this out a little bit further so that you can get a better view, have longer length. And just like you did before, you've got to align that center beam to make sure that's coming back off. And you want to shift it. The best way to find this is when you see that both the reflected beams are converging on the center beam is pretty much when you have what you're looking for. It seems to have it there. And then you do the same thing here. Mark, mark, mark. Lines for the incidents first. And go far out as you can so that you can have a nice straight lines. And then make some markings for you kind of get in your own way with this, so you want to figure out how to make that mark. Go past. Nope, that's not right. This is 1. Go past that point, but do not mark the focal point. It's very tempting to want to mark the focal point. Don't do that. Let your drawing of the lines mark the focal point for you. So make sure you don't get the wrong points marked. Mark it there. There's your focal point. And then you simply measure the distance in millimeters from that to the surface. In this case, I'm getting about 6 centimeters. You'll record that in this case for each of those. If for some reason the reflected lines don't converge, you need to backtrace the beams into your the region of the optic and see if they converge on that side. For page 2, you're now looking at lens objects. You'll take your trapezoid and place it wherever you want on here, however you like maybe you like that way, maybe you like it this way, maybe along this way, whatever works for you. But once you have it there, mark the edge around it. Now you want to try some different things. I'm drawing it this way, but you may find the orientation better than this one because it gives you more space to work with on your paper. Now, place that in here. When it goes flush, perpendicular to the surface, it goes through and the beam path appears to not be displaced. But if you go a large incident angle, a few things become apparent. So I'm going to turn off the light again. And you can see there's a few different characteristics. Number 1, the beam path is offset, just like with the pencil in the water. Number 2, you've got a couple of reflected beams because the light's reflecting off the surface, just again, like the PreLab. And you can see in there, the beam inside is offset, and then the external beam is offset from the original pathway. So as you did before, you'll mark along the pathway and then continue with your measurements. You'll want to extend your marks as far as you can so you can get good measurements with your protractor. Again, having a second sheet of scratch paper on the outside, kind of tape down to it for a few moments, will probably help. For your final 2 optics, you'll want to place your beam like so. That's better. Then try to align your center beam line of the 5 points along the center axis that's drawn on the paper. Then you place your lens on there as centered as you can. Doesn't have to be perfect, but the goal here is, and you probably want a second hand to help you with this part. But you can see that they kind of all converge over there. Now, with your partners holding that in place, you mark your places. But here's the catch. Notice carefully the focal point as I block particular beams. I'm going to block the inner 2 beams. And you can see that those focus point, these appear about there. But when I block the other 2 beams, you see the focal point is much further. So this is your indication of aberration. You'll want to mark your inner beams first in the usual way. Mark the focal point, measure the focal point, then do the inner beams as a separate one. Block the inner beams and measure the outer beams. And you'll see that this is your aberration point, this is your actual focal length, and this distance here is what you record in your aberration field. For your final object, this is a bit of a different beam path for you. You saw something like this with the convex side of your mirror for the concave shape of your lens. We place this here. You see the beam paths broaden, which means that the focal point is going to be on the other side of the optic. How close? Well, you see that's going to go straight off of your page. So let's move this to here. Again, you can see that they don't appear that they'll converge on the same page, but you might have a good chance with this point here on your page. I have the beam set up on this side. You might try the other side and place this optic here, but you'll notice that you don't have as much light here to trace backwards as you need. You could try it at this position, but there's a few different combinations until you've got a good place where you can extend the beam backwards and find your focal length of this optic. All right, great. Well, thanks again for joining for another walkthrough. I'd like to thank Garrett for joining us today and walking us through the theory. And if you have any questions about the theory, about the concepts, or about the wave and particle nature of light, make sure that you ask any one of us, me, the TAs. Make sure that you take advantage of the Physics Help Center for your homework. And until next time, we'll see you in the lab.
Did you know that cats like lasers?
Do they? Wait, maybe green or red? Do they have a favorite?
I don't think they care.
Really? Okay. Oh, shoot. I didn't even put any of my frames up. Haha. Good luck editing, James. All right.
So here in this example ray diagram, we have a concave mirror, and we have a concave mirror. So we have a concave mirror here. So drawing a ray diagram is.
Yeah, I know that.
I can't talk.
So now I've noticed, like, whenever I do the outro, my theme music starts to play in my head. All right, so that's right. I'm taking a video of me cleaning my glasses, lenses. Always check your optics. That is from Real Genius. Val Kilmer, great movie, 1984. Big popcorn scene. Check it out. Do this differently. Have my eye closed. Had actually my eye open. I should probably not talk while I'm doing this. And that does it for this week's PreLab. I don't know what I'm doing.
Now that you've drawn all three rays, you'll be able to see that all of the rays have converted on one point. Not converted.
They come over to the good side.
You'll notice that your object is at a different distance. I cannot speak today. And as a result, n is always less than 1.
Right.
I said less, greater than 1.
The Candyman can, 'cause he sprinkles it with love and makes the world taste good. We watched Willy Wonka the other day.